Anyways, so problem number 3. We've got a conical cone. Or tank. Alright, the conical cone. That doesn't make sense. Conical tank. And it runs out of that tank, so there's water. I'll use blue. Alright, so there's water in there. And that water is leaving at 9 feet cubed per minute. So if water is leaving the tank, what do you think our value of 9 should be?
It's going into the tank.
Oh, it is? Water runs into a conical tank. Alright, good. It's positive, so water's going there. Okay. The tank stands point down. It has a height of 10 feet and a base of 5. So this height is 10, and this base is 5. How fast is the water level rising when the water is 6 feet deep? So this is 6 feet deep.
Is the radius 5 or the whole base?
The base, this part.
Base radius.
The base radius.
Oh, okay.
What that means is if the cone is upside down, what's the
It
base?
says that in the problem. Never mind.
Yep. And we're looking for dH dt at that moment. Okay, well, what do we notice? So the cone problems are always a little bit harder. So Luke is right. If you say I hate cones, you can think that. These problems are a little trickier. Not too bad though. First off, we have information about the rate in which volume is changing. So any ideas on what formula you could use?
Volume formula.
Yeah, amazing, right? So what's the formula for the volume of a cone? You guys are mumbling, but you know, close to it was right. 1/3 pi. Now it's a cubic, so cube is in the third dimension, so you need 3 powers. And it's going to be r squared. 1/3 pi squared is the base times h. Alright. That's the formula for the volume of a cone. So you need to memorize this.
They don't give it to us on the AP test like they do on the ACT.
I don't know if they give it to you or not. Just know it. You're gonna get. I'm not going to give it to you on my test. So. Okay, so we have this problem, and the next step is always. That is a problem. We have this problem. The next step is to differentiate with respect to what? Differentiate with respect to what? Time, right? There's a problem, though. Well, there's not a problem. Let me blindly differentiate with respect to time, and then you will see the problem. So, derivative of volume is dV dt equals. Now, I've got 2 variables, so what rule do we have to use? Product rule, right? Because it's the r times the h. So the derivative of r squared is 2/3 pi r dr dt h plus 1/3 pi r squared dh dt. Yeah, this is. I'm going to show you how this is not going to work out, so you don't have to decide. Right.
Cool.
We know the dV dt. We know 2/3. We know pi. We know the radius. Do we know the radius?
Yeah. 5.
No, at this moment though.
Oh no.
We don't know the radius at the moment. Maybe we can figure it out.
Do
Do we know the rate at which the radius is changing at that moment? No, we don't know that either. We know h, we know 1/3, we know pi, we don't know the radius, and we don't know dH dt. We're looking for dH dt. That's a lot of unknowns, isn't it?
What a few.
Okay.
If you made similar triangles, could you find the radius?
Okay, yes. That's way faster and easier. So, yeah, nice work. Alright, here. Alright, so Matt stole my thunder in one problem and Kyle the next. Alright, good work. You guys are a good team. The idea here, the reason why cones are tricky is because you will always have this setup of similar triangles. Where this small triangle is similar to the bigger triangle. Alright? So the ratio, so a similar triangle ratio, we know that 5/10 will always be the ratio of R over H. Right? Because The original radius is 5, the original height is 10, and all these triangles are always similar to each other. All right, they're similar because, anyone know? Who could prove why they're similar?
Same angles, same
Angle,
bottom
angle,
angle.
right? This angle they share, and then they're both right angles. There's angle, angle. Okay, so simplifying, this turns into 1/2 h equals r. So h and r are variables, right? H and r represent variables, but I can take this 1/2 h and substitute it in for r. And that's going to make the derivative stuff a whole lot easier. So the volume now turns into V equals 1/3 pi h over 2 squared h, which is V equals pi over 12 h cubed. So we're using a geometry fact about similar triangles to take a potential product rule into something much simpler. It still represents the same thing. They're still variables. All right? R and H are variables, but they're proportionate to each other. So we rewrote R in terms of H. That was the big step here. Everyone understand? Any questions on that? Every time you see a cone problem or any triangle problem, potentially, if you've got two triangles, a triangle inside another triangle, you're going to have this happen. So it happens a lot with cone problems. Sometimes with shadows and stuff, that can happen as well. But we'll get to those later. So now we can differentiate with respect to time. So dv dt equals pi over 4 h squared dh dt. And this is a lot nicer. Any questions on how I took the derivative there? I'm just doing the power on my head, yeah. 3 over 12 is 1/4. And then you guys know how I got 12, by the way? 2 squared times 3. I'm just doing the arithmetic in my head there. Okay, so now what information do we have? We know that dv dt is 9. We know that h is, at this particular moment, equal sign somewhere, equals pi over 4, 6 squared dh dt. So this becomes 4 over pi times 1 over 36 times 9 equals dh dt. Hey, look at that. And then what would the units be? Feet per...
Feet cubed per minute.
Should just be feet.
Just feet. How fast the line?
Volume this is feet cubed per minute. This is feet squared. 36 is feet squared. 4 over pi is a constant. So the feet squared and the feet cubed go down to feet. There's the answer. All right. So, and let me just kind of take you back step by step of what happened. The first problem was pretty straightforward. We just found the tangent, plugged stuff in, it worked. The second problem, we used Pythagorean